Remember something, that's a good thing to remember, okay? So, in case of balanced condition, knowing what we know from there, we have rho FB, which is the steel ratio, that is the steel ratio for FRP. So, rho FB equals area of this FRP, AFB over BD, and that works out to be this, okay? So, based on that, you already have defined, whenever you start working with a with a FRP reinforced beam, the first thing we will do, very first thing we'll do is find out this. What is rho FB? What is balanced FRP reinforcement ratio? That's the starting point. If my reinforcement ratio is larger than that, that's good or bad? So I find my rho FB. If my actual FRP reinforcement ratio is larger than rho FB, is it good or bad? Bad? It's always good. That's what we want our design to be. It has to be over reinforced, right? So if it is smaller than that, there is a problem. Or we will use more complicated method. But always, it will so happen that because this AFB or rho FB is going to be very, very small, almost always you will design sections to be over reinforced section. Very rarely will you design anything as under reinforced section. Does it make sense? So that's another takeaway point. You can remember that. Okay, so that's a good point for break. So we'll come back in 15-20 minutes. Yes, that's what I am saying. That's exactly what we have said. So you have rho balance, you found out some value, right? And my actual rho F, which is FRP reinforcement ratio for the actual design, is greater than that. That's what we want it to be. It's just opposite to steel reinforced concrete. Yes, that's right. Should we get started?
Yes, sir.
Can you hear me in the last rows? You're able to hear me? Okay, so I already explained this, I think, reasonably well because I got all the answers. You know exactly what I'm presenting here. If rho F is less than equal to rho FB, we are able to find out rho FB based on 0.003 strain in concrete, epsilon FU in the strain in FRP. That's the balanced condition. That's the very starting point for us. And then you do your section is under reinforced if rho F is less than equal to rho FB. If not, it is over reinforced section. So ACI has this small table. It gives you some numbers for balanced condition. So if you have steel reinforcement with 414 MPa, Fy of 414 MPa, the rho FB is 3.35%. Okay, and that's for a 5,000 psi concrete, which is 34.5 MPa. So for GFRP, it's only 0.78%. So rho FB is only 0.0078, which is 0.78%. AFRP, it's even less. And for carbon FRP, it's 0.2%. Very, very small percent, right? That's what we expected from our equations. So if the steel ratio of the FRP is, reinforcement ratio of FRP, rho F is greater than rho FB, then we'll use this method. So the first equation is Mn equals AF times FF times D minus A over 2. But the problem here is, what's the problem? We don't know FF. Very good. So we are yet to figure out or find out the value of FF. So once again, we'll start with equilibrium. And The total compressive force is 0.85 F prime C, that's the average stress, you know that. And then depth of the compression block, which is this depth here, times the width, so that will be your total compression. Total tension is AF times FF. So if you rearrange these terms, A equals AF FF over 0.85 F prime C B. The only difficulty is we don't know FF yet. We'll find out what it is soon. So we can derive two equations for a section. One is based on equilibrium, which we did just now. The other one is from strain diagram. So I haven't given you the derivation of this, but you can quite easily derive this based on these two conditions. So once you simplify the two equations and do some substitution and eliminate one unknown, you will get FF in terms of quadratic equation. Simplify for FF and you get this equation here, which is square root of EF epsilon Cu square over 4 plus 0.85 beta 1 F prime C over rho F EF epsilon Cu minus is outside the radical sign, outside the square root sign, minus 0.5 EF epsilon Cu. So epsilon Cu is 0.003. Epsilon Cu is 0.003. So based on that you can find out FF. Once you find out FF, you can plug this into your equation for moment strength. That's all. So that's what we do here. You can rearrange the terms and it works out. We simply rho F FF times 1 minus 0.59 rho F FF over F prime C times BD square. This 0.59 is based on the stress block characteristics. So that can easily be derived if you want to derive. If you just want to use the equation, this is quite.
Sir?
Yes.
Can we use this equation in SI units also?
Yes, I think so. In most cases, it is see this EF. EF is here. It's EF, right? Whereas in the square root term, you have EF squared, right? This is no units for epsilon Cu, right? The next is beta 1, no units. F prime C is in, let's say, MPa. EF is in MPa. So that's MPa squared. Square root of MPa squared will be MPa. And then here it's 0.5 EF in MPa. As long as you are consistent with all the units, you will get the same value. No problem. Yeah. And finally, it needs to be less than FFU. Okay. So that will give you your moment strength for over reinforced condition. Any questions on this? It's highly likely that 95% of the problems can be solved just using these 2-3 equations. That's all. Okay. What about under reinforced condition? For under reinforced condition, ACI gives us an approximate equation. Remember I said, even though this is not, this one is not 0.003, this one here is not 0.003 or 0.0035, it's highly likely it will be less than 0.003, in which case the stress block can be triangular or parabolic plus the rectangle like in IS 456, or it can be just a square rectangle like in ACI 318. So if epsilon C is very close to 0.003, let's say it's 0.0028 or something like that, then it is okay to use a normal rectangular stress block, which is fine. But even otherwise, ACI has given us an approximate approach in which it says just use this depth to be CB. CB or beta 1 CB extends all the way to here, and then find out your average stress is 0.85 F prime C and B times A, and then find out your moment strength based on this approach. It's not perfect, it's not accurate, but that's an approximation which is found to be okay, adequate. Okay, but if you don't use that approximate method, then you need to derive some expressions. So we have two unknowns: concrete compressive strain epsilon c and the depth to neutral axis c. These are the two unknowns, and the strain may not have reached 0.003. Strain in concrete strain at the top fiber is not yet 0.003. Rectangular stress block is not applicable because unless you have a strain at the top of 0.003, rectangular stress block, which is also known as Whitney's stress block, is not applicable. So in that case, you must use actual parabolic stress strain curve or actual stress strain relationship as defined in IS 456 or any other standard parabolic stress strain curve. Okay, you can use any of those for concrete. For FRP, of course, the stress strain curve is linear, straight. That's it. So using those two, we can use this method. So you find out the total area of the stress block for compressive force and the location of the resultant for moment. Those are the two things we need to find out moment strength. So ACI approximate method gives you Mn equals AF FU. AF is known, FFU is known, right? D minus beta 1 is based on F prime C, which is also known. CB is also known quantity, right? That's our starting point. Remember, we started with balanced condition. So as an approximation, you can use CB here, which is not accurate, but which is slightly conservative. That means it's more safe. Okay? CB over 2. That's all. Where CB is defined as epsilon Cu over epsilon Cu plus epsilon Fu times D. Is that clear to all of you? Okay? Any questions? It's not perfect. This equation is not perfect. We know that. But were validated, or the equation was validated with the test result, and they think it's maybe within 5% or something like that. Within 5% in civil engineering is pretty good. What about strength reduction factors? Remember, we said in steel reinforced concrete, the strength reduction factor was ranging from 0.65 for epsilon yt, or epsilon t equals epsilon yt, it was 0.65. And if epsilon t was 0.005 or greater, phi was 0.9. And at that time I said something. I said, remember that over reinforced condition, phi is 0.65. We'll use the same phi factor here. So for compression controlled sections, ACI uses 0.65. FRP will be designed as an over reinforced section, and therefore we will use, for over reinforced condition, for FRP reinforced beams, we will use phi equals 0.65. Does it make sense? It's making a connection, right? And we'll use a factor of 0.55 for under reinforced section. And instead of having a cutoff with only one value, ACI said it's better to have a transition. So they said, let's have a little bit of margin, and they said, I'll tell you, okay, let me finish this thought and then I will come back to that again. So for tension controlled section where rho equals rho FB, tension controlled section, we will use a phi factor of 0.55. For 1.4 rho FB, rho being equal to 1.4 rho FB, we will use phi equals 0.65. Anywhere in between, we will use a transition. So the basis for this is when you are designing a beam with an assumption that F prime C is, let's say, 4000 psi. Okay. Generally these days, with all these admixtures and very fancy stuff, the concrete contractor supplier is always able to meet the target almost always, at least in ready mix industry. If you ask for 4,000 concrete, they will give you 5,000 concrete. If you ask for 5,000 concrete, they will give you 6,000 because they are putting admixtures, so it's very simple for them. They don't care about 20 milliliters of admixture. They just pour it. Okay, it's more than 5,000. I'm fine. So if you have a stronger concrete than what you designed for, an over reinforced section can become under reinforced section. Are you with me? Very good. I really appreciate your understanding this. It's very so if your concrete strength is larger or greater than the specified concrete strength, then even though you designed your section to be over reinforced section, it will behave like an under reinforced section, and therefore they put this 1.4 factor. They pushed it to the right, and then they said, okay, use that as a transition zone. Okay, that's the basis for 1.4 rho FB. So we also have a minimum FRP reinforcement, and of course there is no maximum. Minimum reinforcement is based on AF min equals, it's very similar to what we had for steel reinforced concrete. So now we have AF min equals for SI units, it's 0.41 square root of F prime C over FFU BWD, and remember F prime C is in MPa, FFU will also be in MPa, then only it's consistent. So if you ask me why is square root of F prime C having a stress unit, I cannot explain, because that's what it has been for 40 years, 50 years in ACI. So ACI has many equations in ACI will have a square root of F prime C term, and they assume that is stress units. So a square root of stress unit is stress unit. Can anybody explain that? You cannot, because that's the way it has been. Okay, so don't worry about it. Just plug in MPa units here. Don't try to match the units. That's not going to happen. So here you have square root of F prime C over FFU. Same thing here, 2.3 over FFU. This needs to be in MPa units, BWD. So that will give you minimum AF min. But AF min need not be checked all the time, because we are always designing over reinforced section, right? So if you are designing over reinforced section, there is no real point on checking AF min. But it's a good practice. You are having if you have a spreadsheet, just enter these equations once, and that will remain in your spreadsheet. You don't even have to think about it. Okay. Now there is an exception to this. This you may find useful. Those of you who discussed with me regarding design of slabs, you may find this interesting and useful. What is this? This is an exception. You really don't have to use minimum reinforcement if your movement strength is at least 3 times the required strength throughout the length of the member. Does it make sense? So you are designing a member, and if your movement strength using actual area of FRP is greater than 3 times the required strength, that is factor load effect, throughout the length of the member, then you don't have to satisfy this minimum requirement. So there you can actually go around and use a smaller amount of reinforcement, and that will many times help you a lot. Okay, particularly slabs, because slabs are generally not governed by shear design, therefore you can benefit from using this last exception. Okay, and then if you have multiple layers and a combination of FRP types, you must use strain compatibility method based on the actual strain at each level, and then the corresponding stress from the stress strain curve. So we can do that. Moment redistribution, we talked about moment redistribution yesterday. Plastic